Great. Thanks a bunch. And yeah, I regret not being able to be there in person. I've been looking forward to this week for probably over a year or so. But sometimes life comes at you fast, and I'm glad the organizers were able to fit me in for the last talk virtually. So today I'm going to talk a little bit about, I guess, kind of a perspective talk that loops together some stuff we've been working on for the past few years, as well as some kind of brand new stuff that talks about how we conceptualize data, quantum states, and sort of their relationship to each other, and maybe the role that plays in the landscape in which we imagine quantum computers are going to interact with, say, data more broadly, or perhaps machine learning as a specialized application. And so I'm going to start with a little bit of kind of high-level perspective, move into a little bit of quantum data stuff, and then touch on the much dicier topic of what we can really do about classical data in a quantum computer, if anything at all. And so one way to kind of start this is to say, at a very high level, how do we imagine the power of data to some extent? Like, what does it mean to collect data from the environment? So when we do experiments, when we do long computations, perhaps ones that are too long to repeat, so we have some kind of computational data, we can think about how we really do science day to day. So imagine I have maybe a chemical system. I swear this whole talk won't be about chemistry, but this is just an interesting example. If I have some reagents that I buy from some company, maybe simple ones like acetone or ethanol, and I have a bunch of them in a beaker, and I want to ask, what can I make from these? Can I make, a new wonder drug? Can I, make some kind of protein? How long does it take? You can ask all kinds of reasonable questions about this, given your kind of box of reagents. And you can say, well, how long do these take? Does this ever happen? And maybe if you hadn't really studied chemistry or the last few, 100 years of science, you would say, well, at least I know something about the physical laws. Perhaps you're gifted, Newton's equations, you have some kind of molecular model despite not having the rest of chemistry. And you can kind of propagate these things forward in time. You can try to do a simulation, maybe a small box, or you can kind of just mix things together randomly in real life. And maybe you can only afford on a computer one copy. And so you say, well, how do I answer these questions? And if the only thing I know are these equations of motion, I haven't really studied any other parts of science, I kind of put them in a box and I wait and I wait and I wait. And if I never see it appear, do I conclude that it can never be made? Probably not. You'd probably say that's a little bit too bold of an assumption, but it's easy to see that maybe this is not the right way to do things. And so perhaps, one might think that the introduction of quantum computers makes this process a whole lot faster. So quantum simulation is, of course, an active field of study where we imagine some Hamiltonian governing a system. We want to simulate in real time the dynamics of that system going forward. We want to say things about the dynamics, characterize it. This is a rapidly developing field that kind of numerically exact solutions are to some extent available in a time that's sublinear in the number of basis functions as compared to something classically that's kind of exponential. So this seems like an area where for certain problems we can do very, very well compared to classically. And yet we also know other things from kind of the abstract study of quantum computer science, in particular, that even a quantum computer has limits to some extent. So there's this kind of caricature of the no fast forwarding theorem that you can draw, which is to say that anytime you're simulating a physical system to sufficient accuracy, the simulation time has to be some constant greater than the physical time. Otherwise, you could let that system simulate itself and kind of recursively do computation instantaneously. And so if you look at, real time, you go outside, you watch your, favorite lawn chair rust, that chemical reaction can take hours, weeks, or years. And that's after watching 10 to the 23 of these happen all at once. And so if you have a single realization, it's easy to see you're probably never going to see that happen. And so you say, okay, well, what's the point of physical simulation then? And you think in your head about the computations that people actually do, the science that they actually do, and you realize that that's not really what they do. Sometimes we do real-time simulation, and often, though, it's in the service of examining something like a stationary state. So on the left here, we have dynamics, something like the Schrodinger equation propagating us forward in time. On the right, we have sort of its stationary version, which you often see talked about in chemistry and physics for studying ground states, eigenstates. And nominally, both of these have mostly the same input, which is some Hamiltonian. The difference on the left is that you have some, say, initial state you start from, and the difference on the right is you're hunting usually for some particular state. And nominally, we say that the dynamics is a relatively speaking easy problem in something like BQP for short times. And the stationary problem is sort of a hard problem, sometimes QMA hard, QMA complete. So why do we work on the right-hand side so often? And kind of analogous to the arguments I made on the last slide, this is because direct dynamics done accurate enough are sometimes limited to physical timescales. And if I want to know something about a reaction like rusting or things that take weeks or months, I'm not going to wait that long for direct simulation. So I can appeal to what I see around me. This is sort of a general form of data, which is that thermodynamics is often predictive of long-time behavior. I can look around me and see that the world isn't actively on fire, at least not in a literal sense, perhaps in a metaphorical sense, and know that, for example, that T goes to infinity, which is characterized by thermodynamics, is predictive of a long time, much, much greater than this physical time scale that I do actually care about. And so this allows me to kind of leapfrog and make predictions on timescales much longer than direct physical simulation. But complexity theory kind of tells us this can't work for every system. There must be systems for which this kind of thermodynamic study is either extremely hard or kind of breaks down. And so you can ask yourself, well, what is the predictive power of these like aggregate quantities that I can take a subsystem, do a computation, and tell you something very interesting about the future? And you can ask, can all physically interesting questions be answered by some reduced model? And sort of recently, within the study, again, of kind of quantum computer science, we've learned that questions that are as simple as, does a system thermalize? Does it have an electronic gap? Will molecule X ever form from constituents Y? Is in fact so hard that it can be undecidable. And you can say, well, that's a very like strange construction, but you can appeal to this interesting definition of physical undecidability, which is to say, as a system evolves forward in time, there are sudden qualitative changes that cannot be predicted in any way except evolving forward in time and seeing if it happens. And no answer in finite time will ever indicate that that change won't happen. And so you can kind of think about this as, do you know which type of life will emerge? But as soon as you see it, it kind of rules out all the other possibilities of it not happening. And so that piece of data is incredibly powerful in shortening and narrowing what we need to study to understand our physical world. And one way of saying this is undecidability is formally broken by advice in some cases, which is kind of an abstract concept, but data will be a restricted form of advice. And so this really changes the kind of complexity landscape of when we talk about quantum versus classical, or kind of just regular computation versus machine learning, which might have taken in data from an interesting physical system. And it's interesting, I think, to think about those consequences. So within the context of quantum machine learning, so bringing it back to maybe what people here care a little bit more about, we often talk about in kind of quantum computing, computationally limited problems. And I would say that these are problems with sort of simple inputs and a known but perhaps very inefficient computational procedure. One of the most famous, of course, being something like Shor's factoring algorithm. It's easy to see the input. We know computational procedures that, given an exponential amount of time classically, could go through and find you the factors that you're looking for. But we hope that, say, a quantum computer, given those same inputs, can compute with far fewer resources the answer we're looking for. And this kind of idea that data can change the complexity landscape means that you also have to think about, if your problem is amenable to outside input from data, like many physical simulation problems are, you have to be wary that there can be some data-assisted problems. And so this motivates kind of the question of looking at cases where a quantum computer can help you extract data that really change the name of the game without being entirely classical. And so these are kind of data-limited problems. They're very similar to query complexity or other types of constructions. But in this case, we can have problems for which if I turn on my, say, quantum sensor or thing that extracts data, and I only live for some finite amount of time, so I can only give you so much data, and I cut you off, in some cases, a quantum computer can tell me the answer relatively efficiently, and the classical one, without collecting more data, cannot overcome the gap even given infinite computational time. So this is kind of a nice unconditional advantage to have where you can find it, and it fits nicely within this landscape of how we understand data as changing things. And so maybe a motivating example for why this is can be such a problem is this very simple construction. So if I just have some quantum circuit, so I haven't defined a lot of things because I feel like there's a good amount of background in the audience, and you'll just take kind of the normal quantum unitary and circuit notation. So if I'm just given some circuit, it doesn't have to be a quantum neural network, but it could be, and some classical input in this case that I just pop into the amplitudes of a quantum state. Say there's n qubits, and I'm going to put p, which is much smaller than n, like this 2 to the n space, and dump my classical state into that. And so my task will be, of course, to compute the output of some expected value in many cases. Maybe O is just a Pauli operator, but this sort of U, Q, and N can be an arbitrary length quantum circuit. And so, of course, direct simulation of this must be as hard as BQP, because I could have stuck Shor's algorithm in there. I could have made some incredibly complicated, if not exponentially long circuit. And so you're feeling pretty good about yourself. You think this is going to be a pretty good and powerful function. And now I give you a little bit of data for examples from this problem. So I'm going to be drawing these members of this class X randomly and giving you some example labeled data. And if I just kind of rewrite what this output is, I can kind of regroup things and lump the complexity of U, Q, and N into this coefficient matrix. And what I see is something kind of interesting. Even though outputting a single one of these without data would have been very hard, this function is actually a kind of weak function. It's at most a quadratic function on the entries of xi with p squared coefficients. And so what's happened here in this toy case is that with no data, this is an arbitrarily hard quantum circuit given one of the input examples. And with a small amount of data, like a polynomial amount, it's an almost trivial learning task. If I give you new examples, you can immediately give me the answer. And so what this says is, of course, the amplitude encoding is a somewhat weak encoding, but it's something you have to watch out for. If you're looking for a quantum advantage and data is available for your problem, you need to be a little bit conscious of the fact that it's not always true that a hard quantum circuit is sufficient to make, an interesting embedding or a hard quantum learning task. And this sort of motivated a more general study of, this amplitude encoding is weak. Can we say something more general in a complexity theoretic sense about the ways in which these encodings interact with the data and the geometry that the data forms? Because even very hard encodings might not be more predictive for your data. And so if it naturally finds a simple embedding, then you're not really going to have a quantum advantage. But what can a quantum computer do in this case? So we've talked a little bit about the advantages of having data around, and this might make you think that, for example, the role of a quantum computer is only to tabulate this data for simple systems, or that it might be entirely irrelevant if I can do enough experiments in a lab, because if I can empower myself with enough data, I can simply do predictions without ever worrying about it. And so we wanted to look for cases where, in fact, a quantum computer could play a role in this data problem. So it could take in and produce classical data that you cannot produce without this device, that empowers you to do learning tasks that would otherwise be impossible. And so the construction that we're going to have in mind is one very much geared for learning about the physical world. So this is something to the effect of, I have some molecules, DNA, out there in the world. I have a quantum sensor that I've deployed, and I'm going to be interested in sort of examining the states of those quantum sensors and learning about what they tell me about a physical system. And I'm going to compare two scenarios, one in which when I receive that quantum sensor state, I'm allowed to ask the sensor to do another measurement before it collapses. So it have at least 2 copies in memory before I take a joint measurement, and a conventional scenario where I only do one at a time. And similarly, I'm going to learn not only about physical states, but about the kind of processes where I imagine preparing some kind of probe state, sort of exposing it to an interesting process, taking it back. And again, the 2 scenarios will be, I have to do a destructive measurement and get a new copy in the conventional case. And in the sort of quantum enhanced case, I can look at 2 at once. And actually, the conventional case is already quite powerful. Once I've received that copy of a state, I'm allowed to do an arbitrary quantum computation on it before I take my measurement, but it must ultimately destroy the state. And so this work that was quantum advantage and learning from experiments shows that quantum computers can, in fact, with only 2 copies on some tasks, extract data that you can then use in a classical learning model that will be exponentially more efficient than this single copy case. So this is telling you that even very simple quantum memories can allow us to see things in the kind of physical world that might otherwise be invisible. And so kind of to construct this a little bit more concretely, so what's the simplest task we can have an advantage on? And this is just going to be kind of one where we dial it down and try to show that even the states we learned from, we wanted them to kind of be as close to classical as possible because we wanted to know how quantum do these things need to be. So these states will be unentangled but not factorizable. And they're essentially this very simple mixture of the totally mixed state and some Pauli operator. And P is just going to be some general Pauli operator. And everyone is allowed to know both the form of the state, but not this kind of coefficient or the precise Pauli operator. And the task is I'm going to look in these 2 settings. So for conventional and quantum enhanced experiments, it's going to be take any measurement you want on the n copies I give you under those constraints, collect that classical signature of the data that you're allowed to collect with either of these 2 methods, and then given a new Pauli operator, so after the data is done being collected, you're cut off from copies of the state, predict me the trace rho O of that new operator, or alternatively given 2, tell me which one is bigger. And so kind of the meat of the work in this is showing that the best possible conventional experiments do very poorly. So ones where you can receive 1 copy at a time, do arbitrary computation, and then a destructive measurement. And essentially, the best conventional strategy requires on the order of 2 to the n measurements to succeed with any high probability. And a sketch of this is you kind of reduce this to a task throughout the experiment with sort of tree representation of, is this different from the null hypothesis? And the best POVM you can do at every round gives exponentially vanishing returns. And so actually the easier part is the quantum experiment. It turns out that there's a relatively simple scheme for getting at what you'd like here. So if I kind of diagram out these circuit diagrams as receiving 1 copy in the first n qubits of rho, and then I wait around to receive the second copy of rho, and then I just do these Bell measurements that are so common in many schemes, and we'll talk about other schemes in which they appear, and collect 2 n bits out of the end. And this will kind of be a classical sketch of this state. And each of these 2 n bits for n rounds creates an interesting picture of this state. And I can solve this task using a essentially constant number of samples and a computation time that at least needs to touch every sample. So it's roughly kind of linear in the number of bits that I acquire. And this is just to say that the formula is relatively straightforward, even though this notation disguises that. So basically, summarizing the scale of this kind of separation is that if you take any measurements you want on the n copies under those constraints, collect a classical signature, and given some new Pauli operator want to make a prediction, then basically this quantum enhanced or this conventional scenario needs an exponential number of measurements, and the quantum enhanced one is roughly a constant number. And so recall that this is sort of a data advantage in the sense that once I cut off the copies, if I'm below this threshold by any significant amount, with high probability, an infinite amount of computation in the conventional case does not allow me to solve this problem. So it's a nice feature in that no amount of, say, supercomputer time can do anything about this. So it would be nice, for example, to use Bell measurements as a feature in learning. What I showed you before was sort of the exact by hand solution, but too many things in quantum computing, I feel, require you to know the exact and precise solution before starting. It would be nice if we could have some heuristics that would work. So you can ask, can we use this as a feature of a quantum state to learn this task? And say, can state-specific noise or feature boost the performance of an adversary so that we can compare to that too? And so we wanted to set this up in sort of a machine learning type framework, both in the supervised case and in the unsupervised case, where the right side, I should emphasize, is not real data, but we're going to show you some data in a second. And something that's interesting about this that I'll harp on a little bit is that the biggest open question in making these things work, or kind of interesting, is this first step where we're kind of emulating transduction. So if you don't know, transduction is just a word for moving a quantum state from one physical media to another. And we would like to imagine a future where it's easy to take an advanced quantum sensor, hook it up to, say, a superconducting quantum computer, and then do some processing afterwards. At the moment, that's not really reality. And so we have to kind of emulate this transduction. And of course, even if you had this setup, it would be a somewhat noisy process. So we can at least treat lemons like lemonade a little bit and say this emulates the noise that would be inherent in transduction, even in a fault-tolerant world. And so you can kind of see what would happen in the presence of this noise. And so we set this up on the Google Sycamore chip and kind of laid things out in this sort of system and memory qubit. So those two copies, we kind of stagger them in order to emulate this process. So when we do this experimental demonstration, basically we take a recurrent neural network so that we can train on a small size and see how it works on larger sizes. We train on noiseless data up to about 8 qubits. This is kind of an example training cross-section where we show that the quantum loss and prediction accuracy are doing quite well, and the classical prediction accuracy is determined by some information bound. And kind of the most interesting plot here is that if we test up to n equals 20, so 40 physical qubits, what we can do here is check the number of experiments on average you need to do in order to get 70% accuracy with either the quantum model that we're getting out, so this trained quantum model, a rigorous classical lower bound, so the best you could possibly do with any training algorithm, and a training algorithm that you have in practice, which are these gray X's. And you can see that even by 20 qubits, there is this kind of 4 or 5 order of magnitude difference in the number of samples that you would need to take to succeed in the quantum case, where you're allowed to extract these essentially quantum features into classical data before proceeding. And so that makes you feel pretty good about the margin of kind of success there. So you might say, well, that's true, but that was kind of a trivial experiment. If you studied closely the states that we were making, they could have been made in essentially depth 1. There wasn't a whole lot of entanglement across the chip. And so we wanted to do also kind of this process learning. So imagine you prepare a probe state, expose it to some interesting quantum process, and then take your probe state back and then learn about what's happening there. And so the process that we'll look at is determining if something is random time reversal symmetric or a random unitary, or in other words, does it have any imaginary components? And given that it's random, those components will be very small. And this, once again, you'll see a lot of just Bell preparation and measurement, a very suspiciously common primitive. Essentially, you're going to, instead of on the state case where you do a one-sided Bell measurement, you're going to prepare the Bell state first, expose it to the process, and do Bell measurements afterwards. But once again, you're going to get a 2n bit string that defines some kind of feature that is a sketch of your quantum process that you want to learn about. And this was a more interesting experiment. We had to shuffle things around. And when using 40 qubits, we're on the order of 1,400 gates. And so this was an experiment where we were working with more limited fidelities than in the last case, but we're still successful. And this is kind of the part of that I'm most excited about. Like I said, it kind of bothers me sometimes that you really need to know the right answer in many cases for quantum to get everything to work out. So we wanted to do a bit of unsupervised discovery. And so what we wanted to use for our features were just these bit strings that we'd extracted from either our state or our process, and do just a simple feature on those, which is the expectation value of each individual bit and their variance. And then we'll say that this defines some feature for each process that we're learning about. So we're going to take maybe 1,000 samples in the case of the conventional and 500 since that preserves the number of copies in the quantum memory case. And then we're just going to use a very simple similarity kernel, some squared exponential, and do one of the easiest unsupervised learning things you can do, kernel PCA. And what we find is that in the conventional case, basically, when you have both of these classes appearing, if you eyeball it, you would say, well, there's no real difference. They're probably up to what we've measured here about the same process. And if you plug in, though, the kind of quantum enhanced data, it becomes very clear that two distinctly separate things are going on. And this is kind of from real quantum data, even with that amount of noise. You can really see, maybe you haven't learned what these processes are, but you can now pick representatives from these classes and say, well, this is worth diving into because clearly there's two very different things going on. So this makes me feel like early quantum devices might be very powerful in kind of assisting us in learning about things in the physical world that would otherwise be somewhat invisible. And just to kind of belabor this primitive a little bit, so we can kind of imagine that even in a future where we have a fully fault-tolerant quantum computer, if we're indeed doing quantum data processing and it's coming from a natural source, that data is going to come in corrupted. It's not going to be error-corrected in nature, most likely. And so we have this kind of model, in some cases, of uncorrupted data plus some orthogonal errors. And there's been some techniques in the literature for kind of sampling from rho squared, which under this model of errors kind of purifies your state and gets you a lot more data. And the exact subroutine that uses is, in fact, the destructive swap test that we're using here. And so that's kind of interesting, in part because now if you use that operation as a generator, so if one swap is something like virtual distillation, and the swap as a generator, in fact, is the subroutine for quantum PCA that can extract out dominant singular components. And so we prove in this work, though we don't do an experiment because it's kind of complicated, that an exponential number of copies are required to learn the principal components of these states. And this kind of tells you that one very natural thing quantum computers do is for truly multi-qubit states can do a sort of purification that using just conventional measurements would scale exponentially in the number of qubits. And I feel like this is a capability that hasn't really been exploited to its full extent in the lab today, essentially. So what's the big problem, of course, is what are truly multi-qubit quantum sensors, maybe sensor arrays. So if you look around, it's interesting because quantum sensors are perhaps the largest quantum technology maybe at the moment meant operating in the quantum regime that people pay for in order to actually use them in real applications. But many cases where you're looking at these different kinds of quantum sensors, you'll see that they're essentially single qubit or ensemble of single qubits. There's a few experiments that essentially do, in the lab today, try to use things like GHZ states to get Heisenberg scaling. But this is sort of like stretching a single qubit into many for kind of the estimation of a phase characteristic. What we'd really like is where are the truly multi-qubit quantum sensors and what do we learn from them if we can do these kinds of measurements? And this is not something we've had a super concrete answer on, though we're making progress towards sort of more general measurements of this variety. But you could imagine if I have this interesting array of quantum sensors and I can directly transduce the state, what can I learn about the physical world that would otherwise be inaccessible? Can I really put a label on that? And you can say that, well, making these sensors is hard, but I would say it's a bit of a chicken and egg problem. People aren't very motivated to make these crazy multi-qubit sensors if they don't know it does some amazing thing for them. So if we can really kind of motivate their development, I think this could be a great intersection. So just to kind of wrap up the quantum data part of this, my punchline is that I really liked these experiments because it told me that if we could find a suitable data source, kind of our cloud and noisy computing devices today allow us to learn things that are otherwise inaccessible. Exactly what those things are in physical systems, we still need to find out. And in this kind of work, we do a lot of work towards proving that even very simple quantum states can demonstrate this. But I think really the next steps to be done are to inspire work on quantum data sources, expand these sets of measurements, and really understand how this interacts with the physical world, essentially. So that's quantum data, of course. And I feel like there's a lot of people that wouldn't poke too many holes in almost anything you say about quantum computers processing quantum data. Seems like a very natural application. Many of the proofs are unconditional in the sense that you're not even relying on complexity theoretic assumptions, and it sounds very nice. But, this is a conference or a workshop on machine learning, and many people have seen the data that comes from the real world and know that it does, in fact, look quite classical in many cases. And really, this is the definition of a bit of a high-risk, high-reward endeavor in the sense that many people who work in the field for a while look at classical data and think, well, it's probably going to be basically impossible. There's no real good intuition for why this would do much, much better. But, if you succeed in any way, people really like that. And there are a few pieces of evidence that quantum computers might help for classical data. So, for example, sampling from hard distributions with compact circuits learning problems with provable advantages based on discrete logs, advanced linear algebra routines, things that enhance gradient descent, but a lot of pieces of evidence that those carry a lot of caveats and that they might be hard to achieve in practice. And of course, we all remember our first days opening Nielsen and Chuang, where we stick in features of classical data into log n qubits. We get excited about the compactness, and then you read about Halevo's bound limiting you to getting log n qubits back out, and you get very sad. And as I mentioned before, a naive amplitude encoding and expected values also limits you to quadratic function on data. So if you're not clever, these are pretty weak models. Of course, people have now worked a little bit on multiple calls to that, especially in a NISQ regime called sometimes data re-uploading, where you can get trigonometric functions and higher order polynomials on bounded intervals. But some of them are hard to design, and it's hard to see once you have it down there, like, why would a quantum computer be better at doing this classical function that I've now designed than the classical computer? And of course, in fault tolerance, it's about as easy to encode this kind of toy state, which in one step gives you, say, all the features you would want along each dimension, and then you can do like any nonlinear functions you want on one dimension, and we can talk about cross functions later. But the big elephant in the room in almost all of these is once you start doing an honest computational accounting, just putting the data into the quantum state or into the routine often scales with n. So even if you're in log n qubits, you already have spent a lot of energy to the extent where it seems like an exponential advantage is already off the table, because many classical algorithms scale like n or even sublinear. And why is this? Of course, current premier models, how many parameters and how many data points do they take in? They take in something like hundreds of billions or trillions of parameters, and often a similar number of data points. This is kind of at a point that Amira was making in the last talk, which is then if you have any component that even scales quadratically, everything is over for you. And so for a long time, we've worked in parametrized models on the hope that you're going to get a much more compact representation in the quantum case because of this high dimensional Hilbert space. But you have to be a little bit careful, because if you counted in classical probability space, you'd be in the same dimension, just with a lot less convenient constructions. So this is a bit tricky. And so when the number of key parameters is something like 10 to the 12, any scaling worse than linear is already catastrophic. And this could be true in the quantum case as well, as soon as we start counting even the cost of putting the data in. So what are we to do? What should we do here? Is there any hope of success? Well, at least as one trial, we can start thinking about a little bit of a different computational model, and you can fight me on whether this is fair or not. I'll get more exaggerated as it goes on. So basically, loading data is always going to scale with n. Is the advantage lost? But is it ever reasonable to discount the cost of data loading? And how much can you discount the cost? So what do I imagine here? Imagine you have some interesting quantum data center, and as you're collecting experimental data, you're sending it to this data center, and all it's doing is creating these data states and holding them. So we know that they're very compact, or at least in an ideal case they are. Remains to be seen what you can do with them. And there's even these interesting theorems called the mass production theorems, which if you're doing one of these like very heinous state preparations where you need every single component, it turns out the cost of making any number that you want is about the same cost as making one, which is kind of surprising. But you can keep these kind of sitting around and then deliver them to a user when you feel like it. And the question is, well, under this model where I've totally discounted the production of state creation, or at least I allow some amount of pre-computation, what can we do? And classically, we of course use caches, database indices, lookup tables, often not to change asymptotic complexity, but practical time to solution. If I can do some preparation, you give me an input, and now my timer starts when I receive the input, but I can use all of that pre-computation. Maybe I can do things much faster. And so we sort of worked on this in a sort of efficient pre-computation model, where if a normal algorithm gets in some inputs x, y, and rho, and outputs some quantum outputs, versus a pre-computation model where you're allowed to do any polynomial kind of pre-computation quantumly and classically before receiving your final input y. This allows you to do some tasks a little bit faster, it seems, once this is your cost model. And so we know that there's been some work on letting rho define a program, so kind of using quantum data to define quantum programs. And there's ways of consuming these copies. And there are, in fact, ways of one example we give and work out in this model that I won't talk a lot about before I move on to communication, is that you can use this to do a stored state reflection. So many people worry about in the kind of quantum linear systems algorithm that many people here are familiar with, not only things like the condition number, but if you have an interesting state B to prepare, this can also dominate your complexity. And so if you have these kind of pre-computed Bs, you can get away with a lot and sort of do things a little bit faster. And the open question here is, what is really the full class of uniquely quantum precomputations we can do to accelerate time to solution? And this could be data in a machine learning model, but it could also be a more general algorithmic concept. And so if I'm really willing to kind of push the envelope of changing my model of computation such that I'm going to allow any kind of computation, but maybe think a little bit about communication. So there's this model of communication complexity where the only thing you count is amount of bits or qubits exchanged. Each party is allowed to do as much compute as they want. And maybe this is not such a crazy model because today we are kind of data and communication bound in many large scale machine learning systems. So perhaps we'd like to think about this in the future. And the problem is you often have two parties. Alice has X, Bob has Y, and we want to compute some joint function f of x, y, and we only are counting cost in terms of bits or qubits. And in spite of Halevo's bound, there are in fact known cases where some problems can be solved by sending log n qubits in place of n bits, so an exponential advantage despite that essential extractable information content being the same. The most canonical of which, to which we do our reduction, as well as previous works on linear regression have done, is called Raz's problem. So there's some input vector x of size n, some measurement that Alice has that divides the space in two, so m0 and m1. So because it divides the space in two, you can think of this as just a unitary rotation of a Pauli operator, where I get the notation correct in that case. And Bob has some rotation matrix of a unitary. And so Alice has her vector, sends it over to Bob, who rotates it, who sends it back to Alice. And she wants to say, is it in close to M0 or close to M1? And of course, from this construction, it's pretty easy to see the quantum case is just this measurement that you perform. And classically, you can lower bound this as requiring square root n bits. So this is an exponential separation and one that sort of forms the basis of a lot of communication advantages within quantum computing or quantum communication. And so you might say, well, this all seems a little bit fantastical. It's hard enough to build one quantum computer. Why are you now talking about building a bunch of them and linking them together, or even maybe connecting distant ends of a single one? And I would say that the way we're actually designing our architectures today, we're not probably going to print, football field sized chips. We're probably going to loosely link, even within a single data center, different chips together just for engineering reasons and other reasons. And thus, chips are already sort of acting as both computers and repeaters within a single data center. So my kind of bold, probably controversial conjecture is the ability to make good quantum networks will be roughly coincident with good quantum memories. And the requirements beyond quantum memory, like the heralded transduction fidelity, entanglement distillation, are actually relatively modest once you have the device. There's even some prototypes showing that you can do things like this today. What we really lack is compelling end-to-end costed out applications that say, if you built a quantum network, this would be amazing. We, of course, have things like quantum key distribution, but people poke holes in that. And it's really, I think, kind of like Shor's algorithm motivated the development of quantum computers in many ways. We're really waiting for an extremely compelling quantum network application to say we're going to spend as much in quantum networks as quantum computing, though this is already sweeping under the rug that the investment in quantum networks right now, I think, is at least a third the investment in quantum computing. So it's not like people aren't attempting to build these things. And so in this case, we're going to talk about taking a quantum or a machine learning model and distributing it over to these nodes, which is not so far from these compositional models which people use in classical machine learning. And in this paper, we're showing for an expressive class of functions, we find an exponential quantum communication advantage in the problem of inference and gradient determination. So what's the hard part about this? So why can't you just stick easy things into Raz's problem. So I think one thing worth thinking about for just a second, which was alluded to a bit in Amira's talk, was communication advantages in the strictest sense require each of these M and V to be complicated. And so this has prevented, I think, a lot of near-term demonstrations. And what I mean by complicated is they have to really be specified by a size n by n non-trivial circuit. So exponential depth if you're compiling into gates. Why is this the case? So if M or N was generated by a short circuit, so polylog N and white box, it suffices to simply send the circuit description to one party or the other, and you complete it. And even in a black box scenario, the same kind of covering net argument that Amira used says that it suffices to send Clifford classical shadows to beat this problem. So this seems a little bit disappointing because if I'm sitting purely within this communication advantage seat, this kind of feels like it's going to be a bit impractical. But remember that quantum data center argument that if it's just the length of the data, I might sometimes be willing to do this. And also the kind of other light at the end of this tunnel is despite there being a lack of a communication advantage, it doesn't preclude a computational advantage. For example, if you made them sort of pseudo-random states, it might still be hard to do these tasks with a low amount of classical exchange of information. And kind of another complication is that kind of like the power of data arguments we were talking about before, we're often doing classification or prediction not on random sets of points. Maybe it would be nicer if we were, but in many cases, we're trying to classify things that are in some sense classifiable, like the problem is actually doable. And so problem structure, it turns out, can degrade advantage in these kind of complicated communication cases, even if you have very large matrices. So one of the things that we show in this work is that if you have sort of distributed linear classification and you want to know basically which class some object is in, so you're going to compute this sign of x or y, and the margin is sort of reasonably large, then the quantum communication complexity of this is greatly affected, as well as the classical one, by the size of this margin. And so just to give you the punchline, if the classifier is really good, and as I add features or data points, the margin stays roughly as large, the classical and the quantum complexities are still about order 1. So there's no possible advantage that you can get. And this comes from structure in the problem rather than any fancy tricks that one uses with shared randomness or anything like that. So this is to say it's a little bit nuanced, but there are some exponential advantages, or it would seem, in more general parameterized models. So we wanted to create some general model where we could conceptualize what most people do in, say, just parametric quantum networks today, where you have just a product of some, say, data re-uploading component like an A, where Alice has access to maybe classical data and a sort of an initial quantum state, and Bob is maybe doing more mundane rotations or something like that. And you're going to pass the state back and forth with these kind of trained weights and perhaps forms of analogous nonlinearities, and you're just going to have a loss that's a simple expectation value. And so problem 1, we're going to have some kind of estimate that we'd like to compute at the end of this circuit, where we have this distributed, Bob has his parameters, Alice has her parameters, and distributed gradient estimation. And sort of the punchline of this will be that the classical communication of both of these requires at least something like square root the dimension of the space, or kind of the number of layers. In the quantum case, the algorithm is sort of obvious. You just sort of communicate the qubits back and forth. Alice and Bob do their respective gates. Again, we're discounting the cost of actually doing the gates. We're only counting moving the data around. And I'll save you the kind of detailed description of this, but the gradient communication is cheap as well, it turns out, by using kind of variants of shadow tomography that were in the last talk. And so how expressive are these models? This is one of the first things I think people ask when they look at quantum neural networks, because we feel constrained by this idea that transformations are largely unitary and thus mostly linear. And so you can say, well, data re-uploading lets me do some nonlinear functions, and this has been worked out by papers by Maria and others. In this case, we show a little bit of a tighter convergence bound in the sense it's not just asymptotic, but the return on these. Basically, for each dimension of your feature, these types of networks can be quite expressive, especially by using those sorts of Fourier states that I began with. And there's not too much to take away from this other than for smooth functions, this object is quite expressive while maintaining this communication advantage. And we kind of get a natural privacy advantage as well, which is just this naive application of Halevo's bound, that if I'm pushing this quantum state back and forth and there's an eavesdropper, or I don't want Bob to know too much about the data before computing my estimate, then it's somewhat secure in this kind of general sense. And so this expressivity, though, is a little bit of a double-edged sword. You kind of recall I briefly threw up this particular state at the beginning, and I didn't tell you a whole lot about it. I also used kind of bad notation. That should be a subscript k. But if we want to do this kind of Fourier expansion of a data point x along each component, then this thing only needs like log n, log m qubits, where m is the number of Fourier modes along each dimension, and n is each of the dimensions of the feature vector. But similar to amplitude encoding, I've made a fancier amplitude encoding, but cross features are only quadratic. It's not complete across n dimensions. And if I just do a bit of counting, this tells you that if I need the full n-dimensional Fourier state, that essentially I'm writing down n log m qubits, which is what I would write down if I just transmitted you the classical description of each of these entries of x. So this is kind of telling you there's some weird Goldilocks regime here, where linear simple classifiers that are quite robust are too simple to give you an advantage due to problem structure. And incredibly expressive models made with data states like these, I'm not saying there aren't other ways to do this, contain too much information for there to be a communication advantage, because I could just send you the classical state. And that suggests that there are maybe some of these expressive states in the middle where the Fourier modes aren't maybe as uniform, but are selectively chosen, or there's another stochastic way of getting them, where we can retain these exponential advantages while also having very expressive models. And so this kind of brings me to the summary and wrap up of the quantum and classical data picture. So of course, quantum data that we all sort of believe in, at least I do, if we could find a suitable data source, our cloud devices today would be enough to learn things that are otherwise inaccessible. And I think that's a very rich area of exploration, which measurements we can do, what we can do with them, and how does it line up with things we measure in the real world. In the classical case, things are, of course, much harder, but the stakes are much higher. So data, of course, and its presence at all changes the landscape of quantum advantage. But if we can accept some future where quantum data states are stable and computers are networked, then maybe these significant communication advantages or privacy advantages or other ones we haven't really thought about in this kind of precomputation vein can still be quite powerful. And I think this is worth thinking about a little bit, even if we're not willing to give up on the computational advantages quite yet. So with that, I'd like to thank everyone involved. And this is kind of the references for what I talked about for most of the talk. And with that, I'm happy to take any questions, and thank you all for listening.